All right, so we were talking about the frequency, wavelength, and velocity of the light in last class. So we continue from there today. So I am in the fourth slide from last lecture. So uh, there are only 7 kind of light we can see with our eyes. So they are violet light, we can see this with our eyes. Violet, we can see with our eyes. Indigo, blue, green, yellow, orange, and red. So this kind of, there are 7 lights that we can see. So all this what we are seeing in this room is the combination of those 7 lights, and we can see this. But there are a lot of lights below this one. So we call below this one is the ultraviolet region. So in ultraviolet region, what is going on in this room, we don't know. So we can see there are a lot of lights there. What is going on here, we can see. Yeah. So who can see this one? This kind of light, ultraviolet, and below those lights, the animals, the ants, birds, maybe dogs, they can see those kind of light. And how about above it? So there are a lot of rays above this one, like the radio wave, microwave, TV waves, and all other kind of waves we call infrared. So above it, there are a lot of other kind of the light, so we can't see those. The human being cannot see, but maybe the animal can see, the bat can see, the eagle can see. So other kind of the organism can see those kind of light. Yeah, or we need to make the instrument if we want to use those kind of the rays. So this guy has this violet light has the frequency like this, like this. So many peak within short interval, right? So, but the red is like this. So this one, this wave is like this. The red is like this. The violet is like this. So we can see this one, we can see this one. But if we go to the below violet, the frequency is too high. So like this. So we cannot see that one. So if we go above the red, maybe it looks like this. Like this. So that also we cannot see. Yeah. So too high wavelength here, very small frequency. Too small wavelength here, very high frequency. So this very high frequency and very low frequency light we cannot see. So we only can see the light that is somewhere in between very high high wavelength and low wavelength. So only this reason we can. Other below this we can see, above this we can. Make sense? So if there is a chart here. So whatever I just write those 7 light here. So they are here. So there is small region here. So those light I wrote there. So maybe violet is here, maybe red is here. So something like that. So this region we can see, but this is red here, this is red here, this is violet here. So between violet and red we can see. So from here to here we can see, but these rays are called infrared. We can see what is going on here, we can see. So this is called infrared region. And then below violet we cannot see. Very high frequency this way we cannot see. So these things we cannot see. So we can only see this region, we can see this region, we can see this region. So this way is very high frequency, meaning that these kind of light are like this. The wave is like that. The beyond red, the wavelength of those light are like this. Make sense? Yeah, something like this. Good. So this kind of light you cannot see. This kind of light you cannot see. Probably you can see only this kind of light, where you have certain wavelength and certain frequency. We can see this one, we can see this one, we can see this one. Who can see this one? Probably animal can see this one. Maybe dog can see this one. Maybe cat can see those. We can see. Maybe other kind of organism, bees can see those. But human beings are very limited in their vision, so they can only see this one. Make sense? So if we see the flower with our eyes, the flower may look like the pink. But if the bee sees the same flower, the flower may not be pink. It may be something else because he's looking many kind of light coming from the flower. Yeah. Good. So what are the infrared? Some of the infrared light here. So there are those infrared. Here are these infrared IR. So this gives us the heat. So you are burning the fuel, and now you are feeling the heat. You cannot see with your eyes the rays coming from the heat, but you can feel it, right? It gives us heat, right? So the rays coming from the hot source is the infrared. We cannot see those. And this one is a, let's say, microwave. So you go to the kitchen and you turn on the microwave, and it makes the food hot. Food is coming from the microwave machine and making the water hot. It's called microwave wave. Microwave. So these are high wavelength, low frequency. And then how about here? FM radio. So FM radio. So here are a lot of radios wave are coming in. So if you turn on the radio here, you can listen the radio, right? So, but if you don't have a radio, you can't listen it, right? Or you cannot see it. But if you have an instrument called radio, so those radios can capture those FM in this room, the frequency modulation, and then you can sense there is a radio wave here in the room, right? So we just need an instrument to sense those. And then we have the AM radio. So you can look the radio, and there are some, because this is called frequency modulation, this is called amplitude modulation, and there are some short wave radios. So I think so maybe short wave here, I don't know where they are. So this kind of the rays we cannot see, but we must need some kind of the instrument to feel those rays, to feel those radiations. And then there are many long radio waves. So there are other kind of the radio waves. So you can just capture. So if you buy a radio and to turn the knob of the radio to capture those frequencies, so you need to just change the number there, right? So this kind of thing we cannot hear or see with our eyes, but if we have an instrument, we can feel those. So what are the instruments here? So this is definitely the infrared radio. Infrared, you can just feel that is a heat, and these things you must need a radio to listen to those kind of the TV, the radios, right? You need an instrument to feel this electromagnetic wave. How about this one, high frequency side? These are like the ultraviolet. So this is a violet, so frequency, whose frequency is higher than violet is called ultraviolet. So it's ultraviolet. So you go to the laboratory and there are ultraviolet sensing instruments. So this one is used in the chromatography. In future, you go to the laboratory and you do the chromatography experiment. You try to see with your eyes, you cannot see it, but you light there is some instrument to see the ultraviolet, and that will show that color. Yeah, how we cannot sense with our eyes this one. And then how about this one? X-rays. So you go to the hospital and doctor do the X-rays, right? But we cannot see X-rays coming in, but they can give the image, right? So X-rays we cannot see with our eyes because they have very high frequency like this. Very high frequency. And how about this one? So this is X-rays. Now this is gamma rays here. Gamma rays. So there are other rays. So we cannot see those rays also because they have very, very high frequency that is beyond the limitation of our eyes, and we cannot see this way also. So see, the frequency is highest in this one. The frequency is highest. Frequency is HIGHEST. Highest frequency is highest frequency. It's the frequency is highest in this one. In the frequency is lowest in this in frequency lowest. Frequency lowest. And then wavelength highest. Wavelength lowest here. Wavelength WAVE. Wavelength lowest here. You see that? So wavelength is this distance, very small, right? The distance between this peak and this peak is very small. Wavelength is lowest in this side. And then frequency is very high, like this frequency. The repeats the peaks many times per second, right? And in this side, the frequency is lowest, like this. So there is few peaks here. So frequency is lowest, and the wavelength is long. This distance is long. So the wavelength and frequency are just inverse of each other. So if wavelength is higher, frequency is lower. If frequency is higher, wavelength is lower. One is higher, another is lower. Make sense? So that's what it is. If we measure this one, which wavelength can our eyes see? So here is a 700 nanometer, and here is a 400 nanometer. So our eyes can see the light that has the wavelength between 400 nanometer and 700 nanometer. So 400 nanometer means, so the distance between this and this peak is 400 nanometer. You can see it. If the distance between this one and this one is 500 nanometer, you can still see it. You can see it a lot there. And you can also see if the distance between this one and this one is 700. Make sense? 700. But if here is a 750 or 800, you cannot see now this one. Make sense? Or if this distance between this one is let's say below 400, let's say 390 nanometer, you cannot see. So you can only see the light that has the wavelength between 400 and 700 nanometer. Make sense? So these are the violet, indigo, blue, green, orange, yellow, and red. So they have the frequency, the wavelength between 400 and 700 nanometer. Good? Already. But as I told you, all the light, so whether this kind of light, or this kind of light, or this kind of light, so maybe there is another light maybe having the wavelength like this one, very large wavelengths, but these travel with the same speed. Everything has the same speed. So frequency is different, wavelength is different, but the speed of everything is same. Make sense? So in the last class, I gave you a father and daughter a working relationship, right? So exactly like that, yeah? So one try to move his feet more frequently, that's high frequency, like the long, short leg person, but the long leg person move very slowly, right? The pace is low frequency, right? So just like that. All right, so what is the velocity of all this kind of the electromagnetic radiation? So the velocity or the speed of all these is 3 multiplied by 10 to the power 8 meter per second. So in 1 second, all kind of the electromagnetic radiation travel 3 multiplied by 10 to the power 8 meter per in 1 second. Make sense? So just like how many miles per hour your car runs, right? So sometimes they write like 2.99 10 to the power 8 meter per second. It's the same thing. 2.99 is approximately 3, right? So either you write this number or this number in exam or calculation is the same thing, because 2.99 and 3 is almost the same, right? Good. So either you use this number or this number is the same. The speed of the light. So speed of light is given by c. So we have 3 parameters now. We have the wavelength of the light like this. The wavelength. The wavelength is the peak to peak distance. So this is the wavelength, right? Now, how many peaks are there per second? That is given by frequency. And then when you multiply the frequency in the wavelength, you get the speed. So speed of light, c, is given by frequency multiplied by the wavelength. So this is the equation. Yeah. So, and this number never changes. This number c never changes. That is always 3 multiplied by 10 to the power 8 meter per second. So everywhere, anywhere you go, this number is always same. 3 10 to the power 8 meter per second. So only this number and this number change. So in problem, this may be given, you have to calculate this one. This may be given, you have to calculate this one. Because c you don't calculate, because c is always the same. Electromagnetic radiation. Easy? Good. Now let's do. So I am just in the. I just finished the slide number 5. So in slide number 5, I wrote this equation there. So now let's talk about the slide number 6. So there is a problem here. So I go to slide number 6. Slide number 6. So the frequency of the electromagnetic radiation is 1.19 10 to the power 9, 10 to the power 19. So the frequency is given. So the frequency is given, meaning that it is just if you start to take a point here, and let's say the board is the screen of the TV or something or the instrument. You just look this line here, certain point, certain line in this board, and then you keep looking this line here, and how many peaks pass in 1 second, right? So in 1 second, just look 1 second. So just stay here, stand here, and keep looking along this line, and look, one peak pass, another peak pass, another peak pass. How many peak pass in 1 second? That's the frequency, right? So the frequency is given. So the frequency is nu. That is 1.19 10 to the power 9 hertz. Hertz means 1 by second. So that many peaks pass through this line in 1 second. So a lot. 10 to the power 9 is a lot, a very big number, right? More than billion maybe. So that many these peaks pass through this line when you are watching the experiment. Yeah. So this is the frequency of that light given. That many peaks pass through certain point in 1 second. So that hertz means that. Yeah. 1 by second is a hertz. Sometimes hertz is a HZ is a hertz, a scientist name. So in the honor of that scientist, they give this 1 by second is a hertz. Yeah. Make sense? Good. Now the frequency is given, and then calculate the wavelength. Now wavelength. What is the distance between these two peaks? Any nearest two peaks? What is the distance between nearest peaks? So that we don't know, right? But what we know is the velocity of light is always same. C is equals to 3 multiplied by 10 to the power 8 meter per second, or you can put 2.9 10 to the power 8 meter per second is the same thing. Make sense? Simple. Now we need to calculate the lambda. So what is our formula here? C is equals to frequency multiplied by the wavelength. Now C is 3 multiplied by 10 to the power 8. Now I have this number here. Nu is 1.19 10 to the power 9, and I don't know the lambda. So pull this number down here, and that's your number. 3 multiplied by 10 to the power 8 divided by 1.19 10 to the power 9 is equals to lambda, whatever the number comes there. So this is a meter here, right? The unit of velocity is a meter, right? Meter per second. So that gives you meter. That many meter is the wavelength. The distance between the two peaks is 3 multiplied by 10 to the power 8 divided by the this number here. So you got in meter. Now if you want to convert that into nanometer, you need to multiply by 10 to the power 9, right? 10 to the power, I think minus, 10 to the power 9, yeah. So this gives you, so this is, the velocity is meter per second, this is 1 by second, second cancels, so that many meters. So the lambda is equals to 0.268 meter. So from the distance between this one and this one is 0.268. Easy? So C, even if it is not given the value of the C, you always know that is a 3 multiplied by 10 to the power 8 meter per second. Yeah? And then lambda frequency is given. You can calculate it. So let's go to the slide number 7. All right, so what is in the slide number 7? So there is a problem number 1. Which of the following types of the electromagnetic radiation has the longest wavelength? So there was a chart I showed you in the slide number 4. Just look that chart. So ultraviolet light, So that's highest frequency side, right? Ultraviolet is highest frequency. What is asking? Longest wavelength. So longest wavelength is like this. So you have a chart here. You have a chart here. So this is the visible laser. This is the violet. You can see it. This is the red. You can see it. So between violet and red, there are other 5. So these things you can see it. So this way is the infrared. Infrared. This way is the ultraviolet. UV, X-rays, and then UV, X-ray, gamma ray. So like this, right? And this way is microwave, radio waves, FM, AM. And then what else? So, and the long radio wave, so something like this, right? So that chart is in slide number 4. So look at problem number 1. Which of the following type of electromagnetic radiation has the longest wavelength? Meaning that which looks like this, right? Longest wavelength. Peak to peak is very high. So this way, peak to peak is very small. This way. So this way looks like this one. Like this one. This way looks like this one. So longest wavelength is a red light from the laser pointer, microwave from the microwave oven. So microwave is here. So ultraviolet and X-ray. So we don't go this way. This is a very short wavelength, right? High frequency short wavelength type. So we go this way. Now ultraviolet and X-rays are definitely not. Red light from laser pointer. So laser pointer. Red light from the red is somewhere here. So red light can be seen, right? The laser, we can see that, right? So if you turn on the laser in your home, when you play with a cat or dog, so those are the laser lights, you can see it. So that laser is somewhere here. Now, microwave from the microwave oven. So microwave. So maybe the microwave is the longest. So these rays. So this microwave region is the longest wavelength here among these 4 things. Yeah, among these 4 things, not in everything. Yeah, there are 4 things is given. So microwave is the longest because laser you can see it here. So they are just like this. So microwave you cannot see it. So maybe they are like this. So this is the longest wavelength among these. Yeah, among these. All right. So in the number 2. What is the wavelength of the FM radio signal? And the frequency is given as 91.7 megahertz. So frequency is given. So what is the wavelength of the? So this is a FM radio wave. So we don't know what is the wavelength of this one, right? So we need to find that one. But we know the frequency. So what is the frequency of this one? Lambda wavelength, I don't know. What is the frequency of this one? So the frequency would be, it is saying 91.7 megahertz. So if you open the radio, it says, oh, you are listening to the radio at 100 megahertz or something like that, right? So that's a frequency. So it's a megahertz. So this megahertz, so we cannot use in this equation. C is equals to frequency multiplied by the lambda. C is in the meter per second. So the unit of this is meter per second. The frequency must be in the 1 by second. That's a hertz. So this is hertz. So this is hertz, and then lambda will come in meter. So lambda will be in meter like this, right? So meter will be cancelled, and the second will be the same. Now this megahertz must be converted to the hertz. This is not in the cycle per second term. So I will convert this into megahertz to hertz. So 91.7 multiplied by 10 to the power 6 hertz. So 1 megahertz is equal to 10 to the power 6 hertz. So the conversion factor is 1 megahertz. 1 megahertz is equals to 10 to the power 6 hertz. Hertz means 1 by second. So hertz means 1 by second. So if you stand there and look at a point, the radio wave coming from, let's say you are turning the radio, the radio source is there, and then if you can see the radio, and then look at a point, how many time the radio wave pass through a certain point, right? At 1 second. Is that many radio peaks would pass in 1 second, right? 10 to the power 6, many times that radio wave is passing through it. So that's the frequency. Make sense? So now C is given. That's C multiplied by 10 to the power 8. Frequency is this number, put it here, and the lambda is here. Just here is the equation, and that's the wavelength of the radio. Make sense? So I already did that one, so you can just look that one there. Now let's go to, so I want to change the megahertz to hertz. Other thing you can just do how we do it, yeah. So yeah, it's a little bit difficult, but it's interesting. So now, so far we have talked about three things. We talk about the velocity of the radiation, we talk about the wavelength of the radiation, we talk about the frequency of the radiation. Now we have one more term, that is the energy of the radiation. Energy of the radiation. Energy of radiation. Energy of radiation. So that is the 4 parameters that we need to know in this class. Yeah. So if your radiation is like this, your radiation is like this, long wavelength, peak to peak distance is very high, long wavelength. It doesn't have that much energy. It's like the microwave or the radio wave, the TV wave, the red light, the visible light. So they don't have that much energy. They don't hurt us. Do the light hurt us? No, they don't hurt us, right? So we walk, they don't hurt us. So they don't have that much energy. So if you have the wave like this, not much energy. They don't have not much energy. They have energy, but they don't have not much energy. Not much energy. They don't have that much energy. But if you have the light like this, if you have the wavelength, the light like this, or the radiation like this, you have a lot of energy. So this number is small. The lambda is small. So large energy. This is large energy. So it's like the violet light, violet. You can see it, right? Low energy, high energy. So if you have the wave like this, so like this, more energy. If you have the wave like this, even more energy. So the higher the frequency, those peaks, many peaks per second they are producing, that is a very, very high energy. Make sense? Very highest energy. So even if you go further, maybe like this, even larger energy. So if there are many peaks in that wave, at certain time, that has a highest energy. Make sense? So what I'm saying is, if the wavelength is long, energy is very small. If the wavelength, the peak to peak distance, the wavelength is very short, they have very high energy. They hurt us a lot. So this is kind of the X-ray. This is gamma ray. This is X-ray. This is ultraviolet ray. So if you have a lot of ultraviolet rays, your eyes will be blind, right? And then if you put the X-rays many times in the body, they may damage our organ, right? The gamma rays, if you put more gamma rays in the body by some reason, if you are working in the nuclear power plant or something like that, you hurt your body more. So because they have a lot of energy and they penetrate in our body and they damage the cells. But light is like this, the violet light or the red light. So we are getting a lot of light all the time in our body in this room, right? The visible light. So they don't hurt us. Make sense? So they don't have much energy, but they have lots. So frequency, higher the frequency, higher is the energy. Lower the frequency, lower is the energy. Make sense? So higher the wavelength, lower is the energy. Shorter the wavelength, higher is the energy. So who has the higher energy now? So you can look at the chart that I showed you previously, and that is like this. So we are talking about this one. So this is a visible light. So you have a violet here, you have a red light here. So there are other 5 light here. So totally 7. 1, 2, 3, 4, 5, 6, 7. So this we can see all the time. We are getting this kind of the light in our body, so we don't get hurt. So this wave called the infrared and microwave TV wave. So they have long wavelength. So they don't hurt us. All the time in this room, there is all radio waves. Many radio waves are coming in here, and we just can't hear it. Waves are here, but we can't hear it. If I have a radio, I can turn on the radio, and radio will pick that sound and give us to us, right? So So these don't hurt us. So, but this one, this is a ultraviolet, they hurt us like this one, and then this is an X-ray, so like this one they hurt us, and then this is a gamma ray, large energy. So this way is a large energy, this way is a less energy. Make sense? Good. So how to calculate the energy? So energy is calculated like this one. So energy of the radiation is calculated like this one. So let's say you have a wave, you have a wave like this. So energy is calculated. How much is the energy of this wave? We are calculating the energy of the wave is it's not lambda, it's h nu. So h nu. This is the equation. So h is called the Planck's constant. So Planck is a guy who invented how to measure the energy of the radiation. Yeah. So he said, so how much energy is it? So first of all, measure the frequency, right? I already told you how to measure the frequency. So sit there and look at a certain point, how many times the wave passed through that point in 1 second, right? So that's a frequency. So with Planck's constant is 6.626 10 to the power minus 34 joule second. So he found this constant. So that's always the same number, like the velocity of light. So what is the velocity of light? 3 multiplied by 10 to the power 8 meter per second, right? So how much is the Planck's constant? So Planck's constant is this. So this is h. And then nu is, so how much is the frequency of the radiation which is given? Put that number there. So if the frequency was 3, let's say 2 multiplied by 10 to the power 5 hertz. So just put hertz means per second. So hertz is sometimes write it hertz or sometimes second. So put this is h and this is nu. Nu is 2 multiplied by 10 to the power 5 seconds. So 1 by second cancel, and then there is a joule. So you multiply this number with this number and you get the joule. So just by knowing the frequency, you can calculate the how much is the energy with that wave. Make sense? So just by knowing the wavelength and frequency and then Planck's constant, so we can calculate everything. So what Planck says is a little bit different. So previously we were just studying that light just behave like this, continuously it is coming from sun to us or something like that. But Planck says although light behave as a wave, but he says, Planck says, it might be working as like the ball of light. So this is one ball, this is another ball, this is another ball. So let's say I'm receiving some blue in my body. So maybe the source of that light is just throwing me the ball, like the light ball. So he says it's a quanta, so they call quanta. So maybe the light is behaving sometimes like this, sometimes the light is behaving like the ball. So if I am a light source here, I'm just constantly throwing the light toward you like this. Yeah. So how many ball of light I throw toward you in 1 second? Maybe 1, 2, 3, 4, right? 1, 2, 3, 4 in 1 second. I throw it toward you. 1, 2, 3, 4 light ball, like the green or the blue light ball, right? So Planck say, sometimes the light may behave like this, sometimes the light just behave like the ball of the energy, the packet of the energy. So they call this is a quanta, and from here start the quantum mechanics or quantum science or whatever. Yeah, make sense? So there is a two way of looking the light. Light is behaving as a particle, like the particle coming from the source to us, and sometimes the light behaving like it is coming as a wave, how we see the wave in the river or the lake. Yeah, so there are two things, and we call it a wave-particle duality. Sometimes, so I'm here, like I'm behaving as a particle, right? I'm a ball, right? Or something, particle you can say. But in the science, they call, okay, although you look like a ball or the particle, you are, at the same time, you are behaving as a wave. So there is a wave-particle duality, they call. So this is a house, and we think that this house is a particle, right? A single entity that is sitting there, right? But the big head scientists say, this house is not a particle. This is behaving as a wave. Yeah? So light is also behaving as a particle and wave, and particles are also behaving as a light and wave. Yeah? So that is called the wave-particle duality. One thing is behaving two ways. Duality means two ways. Good. So that's how we calculate the energy of the radiation. Good. Now, this is it slide I just finished. Now, you can just rearrange that equation. So E is equals to h nu. I just give that equation. E is equals to h nu, right? H is a Planck's constant. Nu is the frequency of the light, like this. So I want to convert this frequency in terms of the speed of the light and the wavelength of the light. So wavelength. So how can I do that? So I already told you, speed of the light is equals to frequency multiplied by the wavelength, right? So what I do is now frequency. This term is would be frequency is equals to c by lambda. So c by lambda. So c is this lambda down here. So in place of this frequency, I will put h. This is c by lambda. Now you don't need to know the frequency of the light to calculate the energy, right? So you just simply know the how many nanometer here or the how many meter here. This peak, put that number here, and what is the value of this c? 3 multiplied by 10 to the power 8 meter per second always, right? That's a constant number. So if there is a frequency, you can directly multiply h with the nu, then you get the energy. And if there is a wavelength, you just have to write nu as a c by lambda. C is 10 to the power 8, 3 multiplied by 10 to the power 8 meters per second. H is the lambda is, this number is given here, it is 6.62 10 to the power minus 34, right? So if the energy is given, so out of this 1, 2, 3, 4 things, you already know 3 things, and you just need to calculate 1, right? Make sense? Good. So this is the equation. So with using this equation, let's calculate 1. So in the slide number 10, there is a problem. So in the slide number 10, there is a problem. So let's calculate that problem using this equation. Now I am in the slide number 10, and I'm going to use this equation to calculate whatever it is not given. Wavelength of the red light is 640 nanometer. Red light is like this. So if you measure the wavelength, yes, this is 640 nanometer. That's the lambda. Lambda is 640 nanometer, right? And then calculate the energy of a photon. So 1 photon. So calculate the energy of 1 photon. So let's use, you are given the wavelength lambda here. So you are not given the frequency here. So don't use this equation. If you have given the frequency, you would use this equation. But you are given the wavelength, so use this equation. So energy is equals to, so this equation gives the energy of 1 photon. So like the one packet of energy, yeah? So E is equals to H is 6.62 10 to the power minus 34 joule second, and I have the C. Now C, the velocity of the light is already known. You can write 2.99 10 to the power 8 or 3 multiplied by 10 to the power 8, right? It's the same thing. So let's write 3 multiplied by 10 to the power 8 meter per second. Now this is meter per second. If you look here, this is meter per second. This is joules multiplied second. This is joule second. This is meter per second. Now, what is the value of the lambda? Lambda is 640 nanometer. Now you see here, I can cancel this second and second, but I cannot cancel meter and nanometer, right? So the nanometer must be converted to meter, right? So how do we convert that nanometer to meter? So the conversion conversion is like this: 1 meter is equals to 10 to the power minus 9, 10 to the power minus 9 nanometer, like this. So this one. So I need to convert this nanometer to meter is like this. So let's convert here 640. So 640 nanometer multiplied by, I put that conversion factor in such a way that I get meter and I cancel nanometer. So I put the nanometer down here, 10 to the power minus did I put that factor? So yeah, 1 meter equals to 10 to the power minus nanometer, right? Looks like, so the 10 to the power, I need a meter. Actually, I need a meter, right? I need a meter. So 1 meter divided by 10 to the power minus. Why it didn't work that way? The nanometer should be yeah, 10 to the power minus 9 nanometer, right? So nanometer cancel. So you put that meter here. You put that meter here, and then you calculate cancel the meter, and then you will get the value there. So just try it if it works. So I think I might have done something mistake here in my my 640 10 to the power minus 9. That's right, 640 10 to the power minus 9. Why it didn't work? So 10 to the power minus 9. It should be looking like this. 600 nanometer is equals to 640 10 to the power minus 9 meter, like this. So it should look like this. So meter cancel, and then when you calculate that everything, you get 3.1 10 to the power minus 19 joule. So it looks like this one, yeah? So I don't know why that conversion happened at this point. I just couldn't erase that. We'll see. All right, so that much is the joule. So this is the energy of one photon. This is the energy of one photon, yeah? So it is asking you the energy of 1 mole of photon. Now, how much is the 1 mole? 1 mole is equals to 6.023 10 to the power 23 particles. So this particle. So this is the energy of one particle. So how many energy there in that many particles? So multiply that with this one, and that give you the energy of the many particles. Make sense? All right. So like this. That's how we calculate the energy of 1 mole. So if you multiply this number, this is the energy of one photon. So multiply this by 6.023 10 to the power 23, and then you get the energy of 1 mole. Make sense? Good. Good. Now, I think that factor what I did mistake was there is like this. 1 meter is equals to not 10 to the power 9 nanometer. It's a 10 to the power 9. 1 meter equals to 10 to the power plus 9 nanometer. That's what that mistake happened previously. Yeah. So that's a conversion factor. Yeah. So I was just thinking something else. So 1 meter is equals to 10 to the power 9 nanometer. So let's say there was a how many nanometers? 640 nanometer. 640 nanometer, and I was converting it into meter. So it's a nanometer. So I put that factor in such a way that my nanometer cancels. So I put the 10 to the power 9 nanometer down here, and then 1 meter up here. Now nanometer cancel, and then this 10 to the power 9. So I have 640. So I want to put this up there. So I put 10 to the power minus 9. This goes up. Make sense? So if you have something like this, if you have 1 by 10 to the power 9, and if you want to take this guy up there, you can put 10 to the power minus 9 like this. Listen. So the previous chapter, why I was confused was I put 1 meter is equals to 10 to the power minus 9. That's not true. 1 meter equals to the power 9 nanometer. Yeah? Good. Alrighty, so we are almost done for this lecture. So I have one concept. Let's look this one. So there is a photoelectric effect. Electric effect. So it's a photoelectric effect is something from which we make the solar electricity. So the light is coming from the sun, and we put our photovoltaic plate there, and then light strike that plate and gives out the electron, and that electron flow is the electricity. Make sense? So how we produce the electricity from the sun is the photoelectric effect. So photoelectric. So like this. So you have a plate here. So you have a metal plate. This is a metal plate, and this metal plate has a lot of atoms, and with those atoms has many electrons, right? Make sense? So this is a photovoltaic plate or the metal plate, like a lithium piece, sodium piece, or whatever, platinum piece, whatever it is, right? So this is like this. This is a metal piece, metal piece, metal piece. This is a metal piece. Now, what you do is give light here. So the sun from the sunlight is coming. So give the light here, like this. So the wavelength. This is the wavelength of this light. This is wavelength, right? The peak to peak distance is wavelength. So some light is striking this metal surface, and what happens is when this has some energy, so they come and hit that electron and knock out this electron like this. Make sense? So you give the light. It is like there is a ball here. This is a, let's say, soccer ball in this ground, and you run here as a light and then hit it this one so that this goes like this. Make sense? Just like that. So this is called photoelectric effect. So why we call the photo? Because we give the photon, meaning that we give the light. And what it did, it just knocked out the electron from the surface, and the electrons start to flow there. Now put some wire here and collect this electron and bring as electricity. Electricity. So this is the solar electricity works that way. Make sense? So this is called photoelectric effect. So what is photoelectric effect? If we put some light of certain frequency in the metal plate, that light is going to knock out some electron out of the surface, and those electrons start to fly away. Make sense? So this is called the photoelectric effect. If you hit something with the photon, the electrons are going to jump out from the surface of the atom. So that is called photoelectric effect, and this is how we produce the solar electricity. Yeah? Good. Now, can all this kind of the light, knock out these electrons? No, they can. For example, let's say I give a 1-year-old baby a ball here. So there's a 1-year-old baby, and he just run and start to kick this ball. He cannot kick this ball, right? This is pretty heavy. Yeah. But if you are like 18-year-old, you just come here and hit this ball, and you easily can knock out, right? So only those radiation can knock out this electron who has more energy, at a certain level of energy. But if these radiation have a less energy, they cannot knock out this electron. So that is called the they call the work function. The work function. So for example, this electron is bound with certain energy here. So all kind of the radiation cannot knock out this electron from here out, right? So you must, these radiation must have to have a certain minimum amount of energy so that they can knock out this electron. Make sense? So can you teach the chemistry at this point? No, you cannot, because you don't have a threshold. When you have a PhD or you have a master, so when you master, then you will have a cross that threshold and you can teach, right? Just like that. Make sense? Good. So all kind of the radiation cannot knock out the electron from the surface of the from the metal. There must be radiation coming out. This light or the radiation coming and striking the surface of the metal must have certain minimum energy so that they can knock out the electron. Yeah. So that minimum energy is called work function. So let's say 1 minute. So let's say to remove this electron, let's say we need 2 joule to remove. So this is sitting with it's binding with the energy of 2 joule. So that electron, we need minimum energy to remove this electron. We need 2 joule. So if this radiation is coming with the, let's say, 5 joule, so the radiation is coming with the 5 joule. So this needs 2 joule, and then so that radiation is coming with the 5 joule. So how many joule we need here? 3 joule. So with this 3 joule, this electron move away. Make sense? So this is the minimum amount of energy that we need to remove this electron from here, just to break off, right? So they is tightly bound, so we need to break that one with the 2 joule. So and then with 3 joule. So once it break off with 3 joule, this electron moves this way. So this is the kinetic energy of the electron. So this is the kinetic energy of the electron, and this is the work function of that metal, meaning that we need 2 joule to remove this electron, just to detach the electron from here, and this is the frequency of radiation. So this is coming with the 5 joule. So this is the energy of radiation. So energy of radiation. So the energy of radiation is divided into 2 parts: the work function and the kinetic energy of the electron, just like the first law of thermodynamics, right? Second? Good? Yeah, so something like this. Alrighty, so I think we are just done. So I stop this one. So, all right, everyone. Stop recording.